Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the ad impressions and clicks ingestion pipeline, the backbone of every digital advertising platform. We'll cover how companies like Google, Meta, and The Trade Desk ingest billions of ad events every single day with sub-5-second latency and zero data loss. Whether you're prepping for a senior engineering interview or building ad infrastructure at scale, this one is for you. Let's get into it. Hey there! Every time an ad appears on your screen or you click a banner, somewhere in the world a system has to record that event, instantly, accurately, and without losing a single one. Here is the uncomfortable truth. Ad platforms charge advertisers the moment a user sees or clicks a creative. That means losing even one impression event is literally the same as throwing money away. Today we are diving deep into the ad impressions and clicks ingestion pipeline, a system that handles 500,000 events every single second across web pixels, mobile SDKs, and server-to-server APIs. You will learn how Cloudflare workers catch events at the edge in under 50 milliseconds, how Kafka with 512 partitions absorbs the full traffic burst, how Flink enrichment jobs join campaign metadata in real time, and how a light GBM fraud filter kills bot traffic before it ever touches your OLAP store. By the end of this video, you will know exactly how to build a zero data loss ingestion system that scales horizontally on Black Friday, without a single on-call page. This is the exact architecture running at companies like Google, Meta, and The Trade Desk right now. So let us start with the core problem. Think of this system as a high-speed conveyor belt at an airport, one that runs 24 hours a day, 7 days a week, and must never drop a single piece of luggage. Every time an ad is shown or clicked anywhere in the world, this pipeline catches that event within milliseconds, inspects it to confirm it is real and not a bot, deduplicates it so you are not counting the same impression twice, joins each click back to the impression that triggered it, and stores it permanently. The scale here is staggering. We are talking about the equivalent of recording every single heartbeat of 5 billion people, every single day. The fundamental challenge is that you cannot slow down the user's page load to confirm delivery. An ad impression fires and the page moves on. The pipeline must be async, resilient, and perfectly reliable all at the same time. Any data loss directly translates to incorrect billing, misallocated ad budgets, and broken attribution. And in a multi-billion-dollar ad ecosystem, even a 0.1% loss rate represents millions of dollars in reporting errors. Now let us look at what this system must actually do, the 5 functional requirements. First is event collection. The system must ingest impressions and clicks from 3 source types: Web JavaScript SDK using browser pixels, mobile SDK on iOS and Android, and server-to-server APIs for backend-generated events. Second is deduplication. Every event must be deduplicated within a 24-hour window. The same impression or click must never be counted twice, even if the SDK retries on a flaky network. This requires idempotent processing end-to-end. Third is the click impression join. Each click event must be joined back to its originating impression within a 30-minute watermark window. This linkage is what enables attribution. You cannot credit a campaign for a conversion unless you can prove the user saw the ad first. Fourth is fraud detection. The system must filter bot traffic using 3 mechanisms: an IP blacklist, a user agent pattern check, and a click rate anomaly detector that flags inhuman click velocities. And fifth is storage. Raw events go to S3 in Apache Iceberg format for long-term archival, while aggregated data goes to ClickHouse for sub-3-second reporting queries. Here is where it gets really interesting. The non-functional requirements define how well the system performs under real-world conditions. Peak throughput: 500,000 events per second at peak, with the ability to handle 10 times that burst without any data loss. Think Black Friday or a Super Bowl ad slot. End-to-end latency: under 60 seconds from the moment an event fires on the client to the moment it is queryable in ClickHouse. That means the ad operations team can see live campaign performance with less than 1 minute of delay. Durability is 99.999%, achieved through Kafka with replication factor 3 across availability zones, and exactly once Flink checkpoints written to S3. Late event handling. The system must accept events arriving up to 24 hours late. This is critical for mobile SDKs that queue events when the device is offline and flush them when connectivity is restored. Finally, schema management uses Avro with a schema registry, enforcing backward-compatible evolution only, no breaking changes allowed ever. Let me walk you through the full data flow. The architecture has 3 layers, and each one scales completely independently of the others. At the top is the ingestion layer. Browser JavaScript, mobile SDKs, and server-to-server APIs all send events to an edge collector running on Cloudflare workers at over 250 points of presence worldwide. The edge collector validates each event, stamps it with server-received-at-time and geographic metadata, and forwards it to Kafka. Kafka sits at the center of the architecture with 512 partitions, replication factor 3, and LZ4 compression, acting as the system's indestructible buffer. In the processing layer, Apache Flink reads from Kafka and does 3 things in a single streaming job. It deduplicates events using a Redis Bloom filter, it joins clicks to impressions within a 30-minute watermark window, and it scores every event through the fraud detection model. At the storage and serving layer, clean events flow into S3 Iceberg for raw archival and into ClickHouse for aggregated OLAP queries. The key insight is that Kafka decouples ingestion from processing. If Flink falls behind or restarts, Kafka holds the data safely until processing catches up, with 0 loss. Let me give you the headline numbers you need to know cold for any interview on this system. 5 billion plus events per day. That works out to an average of 58,000 events per second, with peak bursts hitting 500,000 per second. Write latency at the 99th percentile is under 100 milliseconds from event fire to Kafka acknowledgement. End-to-end latency from event fire to queryable in ClickHouse is under 60 seconds. Durability is 99.999%. That is 5 nines, meaning less than 5 minutes of data loss per year. The fraud filter rejects approximately 15 to 30% of raw events as invalid traffic, depending on the ad format and inventory source. And the Kafka cluster handles all of this with LZ4 compression, reducing storage costs by 60% compared to uncompressed JSON. These are the numbers that signal production-grade thinking in a senior engineering interview. Let me trace a single impression event from the moment an ad renders all the way through to being queryable. Step 1. An ad renders in the user's browser. The JavaScript SDK fires a beacon post to the nearest Cloudflare worker in under 50 milliseconds. A Bloom filter at the edge immediately checks the event ID. If it is a known duplicate, it is dropped right here before touching Kafka. Step 2. The edge collector validates the event schema, stamps it with server-received-at-timestamp, CFRA ID, and country code, then proxies the batch to Kafka using rate-limiting keyed by IP address. Step 3. Flink reads from the raw event's Kafka topic. An async I/O operator looks up campaign metadata from Redis in under 1 millisecond. The deduplication function checks a Redis set with a 24-hour TTL. If this is a click event, the click impression join operator waits up to 30 minutes for the matching impression using a watermark window. Step 4. The fraud scoring stage evaluates 12 features: click-to-impression ratio, geographic velocity, session length, and more, using a preloaded light GBM model. Events scoring above 0.8 go to a quarantine topic. Events above 0.95 are hard-dropped. Clean events flow to the enriched events topic, then into S3 Iceberg and ClickHouse. The system uses 4 core technical mechanisms that are worth knowing deeply. First is the 2-layer deduplication design. Layer 1 is a Bloom filter at the edge with 1 billion entries and a 1.2 gigabyte memory footprint. It rejects known duplicate event IDs in under 1 millisecond with less than 1% false positive rate. Layer 2 is a Redis SETNX with 24-hour TTL for the roughly 1% of events that pass the Bloom filter, giving exact deduplication with no false negatives. Together, duplicates reaching Kafka are less than 0.001% of total volume. Second is the click impression join using Flink's event time watermark windows. A 30-minute window is held in state, keyed by impression ID. When a click arrives, Flink looks up the matching impression and state, and emits a joined record. Third is the LightGBM fraud model evaluating 12 features in real time. The model is loaded in PMML format and scored inline in the Flink processing pipeline. Fourth is the S3 Iceberg sync with exactly one semantics using Flink's two-phase commit, write to staging files, then atomically commit on checkpoint completion. Let me go deep on the two most interview-worthy components. The Edge Collector runs as a Cloudflare worker at over 250 points of presence globally. When a batch of events arrives, the worker validates JSON schema version 7, generates a ULID event ID if absent. ULIDs are sortable, which improves Kafka partition locality, stamps arrival metadata including CF-ray and IP country for geo-enrichment, applies a pre-bit invalid traffic filter against an IP block list, and proxies to the Kafka REST proxy via authenticated HTTPS. Total CPU time in the worker is under 5 milliseconds. Total client-to-Kafka latency is under 50 milliseconds globally. For the Flink enrichment job, it reads from the raw events topic, runs a keyed process function that checks event IDs via Redis setnx for deduplication, then an async IO operator that calls Redis for campaign metadata in under 1 millisecond, then the click impression join using a 30-minute event time window with watermarks to handle late events from offline mobile devices. Checkpointing runs every 30 seconds to S3, giving a recovery point objective of 30 seconds if the job crashes. Exactly once is guaranteed via Flink's two-phase commit sync protocol. The Kafka and Iceberg syncs only commit after a successful checkpoint. So what are the 5 things you must walk away knowing from this system? First, FireArm Forget with SendBeacon is the right ingestion model for impression events. It never blocks the page load, handles backpressure in Kafka rather than in the browser, and the SDK retries independently. Use synchronous delivery only for high-value conversion events where guaranteed delivery is worth the latency. Second, two-layer deduplication, Bloom filter at the edge for speed, Redis setnx for exactness, gets you to less than 0.001% duplicate rate at 500,000 events per second without expensive distributed transactions. Third, Kafka with 512 partitions partitioned by user ID hash gives you both horizontal scale and per-user ordering, which is essential for attribution window reconstruction. Never use fewer partitions than your peak parallelism needs. Partition count is hard to change after creation. Fourth, Flink exactly once via two-phase commit checkpointing to S3 is the production-grade way to achieve zero data loss in a streaming pipeline. Combine it with idempotent Kafka producers and transactional consumers for end-to-end exactly once. Fifth, always design your fraud filter as 2 stages. A fast rule engine using Bloom filters for known bad actors, followed by a slower but smarter ML model for anomalous behavior. This combination gives you sub-millisecond rejection for known bots and catches sophisticated click fraud that rules alone would miss. And that's a wrap on the ad impressions and clicks ingestion pipeline. We covered the full picture from the load balancer and API gateway, through Kafka for high-throughput ingestion, Flink for stream processing, all the way to real-time serving in ClickHouse and cold storage in the data lake. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.